Hey guys, welcome back to three, part three of Chapter 8 Solutions Chemistry. And today we're going to look at electrolytes. Now we define electrolytes as solutes which can be added to water to form ions and then allow an electrical current to form. So we have come across one of the best sources of electrolytes in chemistry already. We've studied Chapter 3 with ionic compounds. Ionic compounds which are naturally made up of positively and negatively charged ions. Ionic compounds normally form the best electrolytes and many of the strong electrolytes. And we had talked about the rules for ions which are good at dissolving in water in Chapter 3. We had said that we were looking for any compound that contained a group 1 metal. So something like sodium or potassium, lithium, etc. They strongly dissociated in water into their individual ions as they formed a solution. We also had some polyatomic ions which were pretty good at dissolving and therefore creating ions. Things like nitrate, NO3, ammonium, NH4, chlorate, ClO3, and hydrogen carbonate, sometimes called bicarbonate, HCO3. These were some of the ones which we said would guarantee solubility, guarantee producing an electrolyte in solution. And so that chemical, that solute, added to water as solvent, would have a position of equilibrium that was on the far right. Most of the chemical breaks up, dissociates into these individual sodium and chloride ions, or like calcium nitrate, dissociating into these individual calcium and nitrate ions, or ammonium and phosphide ions with ammonium phosphide. So these are our electrolytes. They are solutes which produce ions in solution, ions which are capable of carrying an electrical current. Now the non-electrolytes of the universe are chemicals which are normally covalently bonded. Covalently bonded compounds don't like to dissociate into their individual atoms to produce ions. And that's because if we look at, for example, methane on our list here, we can draw a quick and simple Lewis structure. Carbon at the center, it needs to form the most bonds. We connect it to the hydrogens, and with 1, 2, 3, 4 chemical bonds, we complete the duets of the hydrogens, but also complete the octet of the carbon. However, if these atoms were to dissociate in water and break up and head in their own way, breaking those bonds, we would lose our duets and octets. They would not be stable. So this is why covalent compounds normally don't break up into individual atoms. They don't dissociate. It doesn't make them stable. Now, there are occasionally exceptions to that rule amongst covalent compounds, usually compounds which have really polar covalent bonds, like hydrochloric acid. And most of our acids, which we term as molecular acids, do dissociate, do break up in this way to produce ions. In the case of hydrochloric acid, that HCl strongly dissociates into hydrogen ions and chloride ions. Although, as we'll see in Chapter 9, the hydrogen ion normally piggybacks onto a molecule of water to form a hydronium ion, but it's still an ion. So there are some covalent compounds which are indeed strong electrolytes. The only one I'm expecting you to be familiar with is HCl. Again, it is a very small list. Normally, if the compound is covalent, it doesn't dissociate, it's a non-electrolyte. And we can recognize these covalent compounds because they have just non-metals and metalloids in the chemical formula. Covalent compounds normally don't have metals. And so if you don't see a metal, it's probably covalent. And most of our covalent compounds are non-electrolytes. There's two main factors for deciding whether the electrolyte is strong or not. One is the concentration. We want a high concentration of the electrolyte to produce a high concentration of ions. But of course, it's got to be capable of dissociating in water to produce those ions. It doesn't naturally have those individual ions, positive and negatives, as a solute. It's got to break up. So if it's in high concentration and it's good at dissociating, then it's going to be a strong electrolyte. And that would be things with a position of equilibrium firmly on the right, things like sodium chloride, of course the group 1 sodium metal, making it highly soluble in water, or potassium hydroxide, the potassium making it highly soluble in water and making it dissociate into potassium and hydroxide ions, or the hydrogen carbonate, which was another one of our polyatomic ions in our rules for high water solubility, highly water soluble, so dissociates from the calcium, and the position of equilibrium is firmly on the right again. Again, we could look at an equilibrium constant, a strong value for the equilibrium constant, to tell that it's strongly dissociating and a strong electrolyte. There are some solutes which dissociate but only dissociate weakly. This tends to be relatively weak molecular acids like acetic acid. That hydrogen on the end breaks off, and so we get the acetate ion, CH3, COO to the -1, and hydrogen ions. But it's not very good at doing it. And so most of the molecules stay in this form without dissociating. So there's only a small concentration of these ions, and it's only therefore a weak electrolyte. Hydrogen fluoride, another good example. It can dissociate into hydrogen ions and fluoride ions, but again, it's not very good at it. It only weakly dissociates, and most of the compound stays in this form, still with that chemical bond intact. We can look at equilibrium values for different solutes and compare the equilibrium constant, sometimes called the solubility product. It seems quite small, but we are dealing with a aqueous solution after all, 1.84 times 10 to the -3 for lithium fluoride. That's a pretty good value. We can tell it's a strong value for the equilibrium constant when we compare it to something like calcium carbonate, which is a weak electrolyte, when the equilibrium constant, that solubility product, goes way down to 3.36 times 10 to the -9. That's a very small value and a very weak electrolyte. So looking at some firm examples, strong electrolytes, these tend to be ionic compounds, so things like sodium chloride, potassium hydroxide, molecular acids like hydrochloric acid, which is one of the covalent exceptions, and potassium bromide. Weak electrolytes, as we said, hydrogen fluoride and acetic acid. Also ammonia, NH3, fits into this bracket as well. And then non-electrolytes, almost any covalent molecule that you can think about, be it hydrogen peroxide or ethanol. No metals, covalent, and quite likely a non-electrolyte. So if we look visually at some examples, maybe this will help. Strong electrolyte like sodium chloride, surrounded by pink molecules of water. I'm not sure why I chose pink, but never mind. The solute completely dissociates in solution into individual ions, which are capable of passing around electrons for a current. A weak electrolyte like hydrogen fluoride, some of the molecules dissociate into hydrogen ions and fluoride ions, but the majority of them stay together, bonded, as hydrogen fluoride. And then non-electrolytes like hydrogen peroxide, all the molecules retain their integrity. Nobody is dissociating into individual ions. In the body, we need electrolytes for electrical impulses to drive the pumping of the heart muscle, and even just in the neurons for our thought process and muscle contractions. We have positive ions and negative ions, and usually there's a good abundance and balance between positive and negative. An imbalance of one or the other can cause medical problems. So we need to be able to measure the number of ions in the body. And we usually talk about these equivalents by measuring the number of moles multiplied by the charge for that particular species. So if we look at some examples, if we had a mole of sodium ions, because sodium a group 1 metal, 1 plus charge, and so 1 times 1, that'd be 1 equivalence. Calcium from group 2, that's a 2 plus metal, so 1 mole times that 2 plus charge, that'd be 2 equivalents. Phosphate ions, 1 mole times that 3 and negative 3, giving us 3 equivalents. Or 3 moles of sodium ions, 3 times the 1 and 1 plus, so 3 equivalents. And 2 moles of calcium ions, 2 times that 2 and the 2 plus, giving us 4 equivalents. It doesn't have a positive or negative assignment to it. It's just a raw number. We can also think about a factor labeling method for working out the number of equivalents we have. Usually we measure in milliequivalents because the concentration of these electrolytes is relatively low. So we talk about these milliequivalents with 1,000 milliequivalents to make 1 equivalence. Let me just make myself some space here. So for an example like this, let's see. Yep, 1 equivalence equal to 1,000 milliequivalents. Just keep that in mind. I went too early. I'm not at the problem yet. So some examples. Get my pen up and running. So we've got 2 moles of magnesium ions. Remember, for the equivalence, it's equal to, whoops, bad cue there, the number of moles multiplied by that charge. So 2 moles times that plus 2, that gives us 4 equivalents of magnesium ions. The 0.75 times that 1 plus charge, that gives us 0.75 equivalents. And then the 2.4 moles of sulfate ions, the 2.4 times that 2 in the negative 2, that gives us 4.8 equivalents of sulfate ions. Here's the one I was looking for when calculating in milliequivalents. So 1 liter of a solution containing potassium ions, 182 milliequivalents per liter. How many milliequivalents of potassium ions would there be in just 600 milliliters? So we've got 182 milliequivalents for an entire solution. That's in 1 liter. We've got 1,000 milliliters to make a liter. And we're taking 600 milliliters of the solution, and that gives a grand total of milliequivalents of.
Right, sorry about that. My headphones started to wig out at me and go crazy. It was like the battery was dying. So I switched to my computer speakers. That gives us 109.6 0.2 equivalents for that one. Looking at the ones below, the equivalents for each metal in the compounds below. So we've got 1 mole of sodium sulfide, but in every mole of sodium sulfide, there's 2 moles of sodium. So 2 moles times that +1 charge, that gives us 2 equivalents. Second one, 2 moles of sodium nitride, but in every mole of sodium nitride, there's 3 moles of sodium. So 2 times 3, that'd be 6 moles, multiplied by the +1 charge, so equal to 6 equivalents of sodium ions. And then finally, 2 moles of aluminium oxide, or aluminum for our American friends. But in every mole of aluminium oxide contains 2 moles of aluminium. So 2 times 2, that would be 4 moles of aluminium ions, multiplied by its charge of 3+. So that would give us a grand total of 12 equivalents. Okay, that should be it for the electrolyte section. Let's see. Next section is colloids. How long have we been going for? I think I'm just going to keep on going. Yeah, keep on going. So I'll just roll the 2 lectures into one. So with colloidal properties, we're talking about solutions which have got really big particles, really big, like bigger than a nanometer in diameter, which is pretty big for particles. And they're so big, they often actually catch and deflect light. You've seen that kind of effect if you're out driving in the morning or late at night, and there's a mist or thick fog, and as it scatters the light from your head beam, that's a colloidal effect. You've got these big water droplets in the mist, which are physically scattering the light beam. So these solutions often appear cloudy, like fog appears very cloudy as you're driving down the road. Now, there are a variety of properties which we group together as colloidal properties. The only 2 we're going to talk about briefly are boiling point increases and freezing point decreases, what we sometimes refer to as boiling point elevation and freezing point depression. You take a liquid, a pure liquid, and you add in a solute, that will cause the boiling temperature to elevate and also cause the freezing temperature to depress or drop even lower. But for that change in the boiling temperature and freezing temperature, elevation and depression, the solution that's produced by adding a solute only cares about the sheer number of solute particles. You increase the number of particles added, you increase the effect. Because we normally measure solute particles in bulk, we measure the number of moles of solute particles. And so we often talk about this boiling point elevation or freezing point depression in terms of the number of moles of solute which have been added. Take a look at the 3 examples here. So which of these 3 solutes added to a litre of water would cause the greatest boiling point elevation and freezing point depression? Take a second and work it out for yourself. Okay, let's take a look at the 3 of them. So we're given very similar masses for the 3 solutes, but that doesn't mean we've got an equal number of solute particles, because we need to measure the number of moles. So if we look at the formulas, we can work out the mass for each. 12 grams for carbon times 2, 1 gram for hydrogen times 6, and added to that 16 grams for oxygen times 2. So that gives a grand total for the molar mass of 62 grams Oh, I lost my pen. 62 grams per mole. So that mass of 186 divided by the molar mass of 62, that comes to 3 moles. 3 moles of solute. Look at the second one, 12 grams for carbon times 3. 1 gram for hydrogen times 8. And 16 for oxygen times 3. Sounds like my kids have been tickle tortured. That comes to a grand total of 92 grams per mole. 184 divided by 92, that works out as 2 moles this time. So despite being a very similar mass, we've got 3 moles compared to just 2 moles. And the last one, again 12 grams per mole for carbon times 6. 1 gram for hydrogen times 14. Then 16 grams for oxygen times 6. That comes to a grand total of 182 grams per mole. So 182 divided by 182, 1 mole. Remember, the effect on the boiling point and the freezing point depends on the sheer number of particles. We don't care about the chemical nature of the solute, we just care about how many moles, how many particles there are. And so the 3 moles of the ethanoic acid, that probably stands for, is the winner. Greater number of moles, a greater effect on the boiling point and freezing point. And that's almost all there is to write about freezing point depression and boiling point elevation, with one small caveat which is important. That is that sometimes the solute you add is an ionic solute. Just as we saw with the electrolytes, ionic compounds dissolve in water and dissociate into individual ions. And so we're increasing the number of solute particles. You could take 1 mole of potassium chloride, but that breaks down into potassium ions and chloride ions, so we create 2 moles of electrolytic particles. Sodium sulfide, as we saw earlier, 2 moles of sodium and 1 mole of sulfide. 1 becomes 3 moles of ions when added to water. Aluminium fluoride with aluminium and 3 moles of fluoride ions. That gives us 4 moles of ions. And calcium phosphate breaks up into calcium ions and phosphate ions. So every 1 mole becomes 5 moles of ions. This is what we sometimes refer to as an I factor in the freezing point depression and boiling point elevation. The examples that we'll sometimes look at is with the effect on the freezing temperature of a body of water. And we need to consider what we call the freezing constant, as we'll see in the laboratory. Freezing constant, it tells us that when we've got a kilogram of water, the freezing temperature of water drops by 1.86 degrees Celsius for every mole of solute that's in solution, multiplied by that I factor. So you could have 1 mole of sodium sulfide, but an I factor of 3, because it's breaking up into 3 times as many electrolytic particles. Anyway, more on that another time. So we've got that I factor to take into account. So try these 3. What would be the solute to create the greatest freezing point depression effect based on these levels? Take a second to work out your answer before we go over the answer. Okay, we'll assume we're back. So this time the number of moles has been worked out for you. Remember, this could be a figure in grams, so you'd have to use the molar mass to work out how many moles you've got. But we still have an extra layer of complication in these problems because 2 of the 3 solutes contain metals, sodium and lithium, which makes them ionic compounds. And we know that these ionic compounds dissociate in water into their individual ions. So sodium chloride added to water dissociates into sodium ions and chloride ions. So every mole becomes 2 moles of solute particles. So that 2 has to be multiplied by 2, and we've got 4 moles of ions in solution. If we look at our second one, that's the lithium sulfide. Excuse me as I crudely try and separate them here. Lithium sulfide is also ionic. Lithium sulfide breaks up in water to produce lithium ions and sulfide ions. 2 moles of lithium ions, 1 mole of sulfide. So that gives us an I factor of 3 for ions produced for every mole. So that 1.5 moles is trebled into 4.5 moles of ions. Ionic compounds dissociate in water into their individual ions. Last one, 4 moles of the ethanoic acid again. Actually, it must be probably ethylene glycol. The formula is not right for ethanoic acid. So ethylene glycol. Hello. You ready for bed, bud? I will be along when I finish this, okay? So the ethylene glycol, that's probably what it is. Shh. It doesn't contain any metals, just carbon, hydrogen, and oxygen, all non-metals, and so it doesn't dissociate. So the 4 moles we start with are the 4 moles that we'll finish with in solution. So the lithium sulfide, although having initially listed the least number of ions, least moles, because it dissociates in water, that actually gives us the most solute particles. It would therefore have the greatest effect on the freezing temperature of a body of water, and the greatest effect on the boiling temperature of a body of water. Okay, so work out the number of moles you have, and work out any I factor. Does that solute dissociate in water any further? And that's working out whether you have an ionic compound or a covalent compound. Okay, almost finished for our lecture tonight. Last thing we have to talk about is osmotic pressure. You take 2 solutions and separate them by a semi-permeable membrane. That semi-permeable membrane allows the passage of water back and forth, but it stops the movement of solute particles, which are normally too big. And if there's a difference in the concentration of solute from one solution to the other, separated by the semi-permeable membrane, it can start to create some osmotic pressure. Osmotic pressure is normally calculated by taking the molarity of the solution multiplied by the gas constant, which we saw in the last chapter, multiplied by the temperature. Now, we care about this because our bodies are big bags of solutes in our blood plasma and other solutions in the body, and the cell walls of our cells act like semi-permeable membranes. And so we could see the movement of liquid water in and out of the cell depending on whether there was a difference in solute concentration. This is why when a solution is intravenously administered to a patient has to be isotonic. The solute concentration in that administered solution has to be equal to the concentration of solutes in the body. If it isn't, we'll start to produce some osmotic pressure, as we'll look at in a second. So you can do this in a laboratory. It takes two solutions, put them in a beaker and separate it with a semi-permeable membrane. The water moves from high to low pressure. Normally, the solution is described in terms of the concentration of the solute, but we can still work it out. For example, our two solutions, 5% glucose and 10%. So the solution on the right here is high in solute, and as the solution becomes high in solute, it becomes low in water concentration. The more solute you add, the lower the water concentration. So the 5% solution, which is the relatively low solute concentration compared to its neighbour, is therefore relatively high in water concentration. And the water can move back and forth, left to right and right to left, but it's going to predominantly move from left to right, from high water concentration to low water concentration. Think of the analogy like a waterfall, from high to low. Water moves through the semi-permeable membrane from high to low. So over a couple of hours, or maybe overnight, the water levels in that beaker the following day will have drastically changed. Water moving predominantly out of the high concentration to the low water concentration. Okay. Again, as we mentioned, we care about this because our bodies have cells with semi-permeable membranes. If we look at blood plasma and a patient connected up to an intravenous drip, we need the concentration of solutes in that drip to be equal to the concentration of solutes in the blood plasma. That's usually a concentration of 0.92% as a percentage concentration, or if it's being expressed in molarity, moles per litre, that would be 0.15 molarity. Because that's usually just a saline solution being administered of sodium chloride. So that's nice and safe. That's an isotonic solution, and it keeps our blood plasma nice and healthy. However, if we had a solution which was much higher in water concentration because it was lower in solute concentration, these are solutions that we refer to as hypotonic solutions because they have a water content that's too high. And so as it mixes with the blood plasma in the body, that water from the intravenous drip, that starts to pour into the red blood cells. Probably use black for this instead. So water from that solution passes into the red blood cells and they swell up. This is what we call hemolysis. And it can cause the blood cells to actually rupture and burst, basically. The water always moves from high to low water concentration. Now, on the other hand, we could accidentally administer a solution which is hypertonic. It's low in water concentration because it's high in solutes. Think of a simple solute like sugar. If your kids have got too much sugar in their drinks, then they're going to be hyper during the day. Likewise, a hypertonic solution is a solution that has too much sugar or too much solute, whatever that solute is. And so the high concentration of water comparatively is in the red blood cells, and that passes out of the blood cells into the solution, and losing the water, these red blood cells start to shrivel up. It could be permanently damaged. This is what we call crenation, as they shrivel up. So solutions which are administered to a patient have to be isotonic. We need a balanced concentration of water with the drug to the body. Otherwise, we can cause these osmotic pressures to build. Bad news for the patient. Now, sometimes osmotic pressure is our friend because our body, of course, naturally performs dialysis in the kidneys to get rid of waste products, which it sends to the urine. That's usually waste molecules like urea. But for some people, their bodies can't perform that dialysis on their own. And so we need to put the patient through a series of hemodialysis for a couple of hours, probably 2 or 3 times a week. The blood passes through the machine into this solution of solutes, which creates a large osmotic pressure, and it forces out waste material like urea into the solution, out of the body. That solution can then be collected and discarded, but it prevents large molecules like proteins and red blood cells from being passed out of the body. Usually the solution for hemodialysis is a mixture of sodium chloride, potassium chloride, and sodium hydrogen carbonate. Let's finish on a couple of example problems. So examine the picture below. We see there's been some osmotic pressure in a beaker overnight between the 2 solutions separated by a semi-permeable membrane. Which solution is responsible for each side in each of our 4 examples? 1, 2, 3, 4. Take a second and we'll work that out. Okay, I assume you've paused the video and tried these. Again, even if you're not sure, use your notes, make a guess as you're watching the videos. Take your best effort. Don't just wait for the answer to be revealed to you. Get your brain working. So let's see. Annotation back. Okay, let's use a nice purple this time. So, first thing to look at is the beaker itself. As we can see, the movement of water has been primarily from the right to the left. And so this solution on the right must have been the one that started with a higher water concentration. And the solution on the left had a lower water concentration. Water moves from high to low concentration. Now, if that solution on the right was high in water, it means it was relatively low in solutes. And the solution on the on the left, which was low in water, must have been relatively high in solutes. So for the solution on the right-hand side each time, we just need the one which is low in solutes. So for the first one, a relatively low concentration is the 1% saline. So that would be the solution on the right. The 2% solution, higher concentration and therefore lower water concentration, would have been the one on the left. For the second one, 10% compared to 5%. So the 5% solution would have been the one on the right. And the solution on the left at 10%. Next one, glucose and sodium chloride, both given as a 1 molarity concentration. But of course, sodium chloride dissociates into sodium ions and chloride ions. We know this because it contains a metal. Glucose is organic, it doesn't contain metals. And so for every mole of sodium chloride, there's 2 moles of sodium and chloride ions collectively. So that's the solution with a greater amount of solute. So the relatively low solute concentration was the glucose solution. That must have been the solution on the right, while the sodium chloride was on the left. And finally, 5 molarity lithium sulfide compared to 5 molarity sodium chloride. Sodium chloride, as we see, gives 2 moles of ions, but the lithium sulfide, as we talked about previously, dissociates to give 2 moles of lithium ions and 1 mole of sulfide ions. 2 plus 1, that's collectively 3 moles of ions. There's a higher number of moles, a higher concentration of solutes than the sodium chloride solution. So the sodium chloride is a relatively low solute concentration solution. That's the one which must have been on the right. And the higher solute content of lithium sulfide, that must have been the one that started on the left. Okay, that just about does it for today. So we've packed Friday and Monday's lecture into one big marathon lecture. Yep. So I hope that helped. I'll see everybody soon in the lab. And of course the test is coming at the end of the week. I think we'll do a test on chapter 8 on Sunday night this week, and then again on Monday night. Okay, so no test on Friday night. And the chapter 8 homework is going up tonight, Monday, and that'll be due on, we'll make that Sunday evening before the first, or just after the first test, and the polling questions will be due on Saturday night. So people can look at the answers on Sunday morning before taking the exam on Sunday night if they wish, or wait till Monday night when the homework answers have also been revealed. Stay safe, wash your hands, wear that mask.